Hey yo, what is up guys? It's your boy. Today we're going to be talking a bit more about electron configurations and ground states, and a bit more about how we can configure or describe the electron configuration of ions, particularly cations and anions. So yeah, let's get into this. So in the last video we kind of talked about how in order to kind of give the electron configuration of atoms, we typically need to find the address of the last electron, and that still holds true to this video. So let's do a couple of examples. Let's start off with the magnesium. Magnesium, and we can do this example together, or if you want, you can pause the video. Magnesium has 12 electrons, right? And it's found, if we label our ends, or we label our shells, it's found at n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, and so on. Magnesium is found in the S block. It's found in the S block, in the second column, which denotes that there are 2 electrons. So we can say the address of the last electron in the magnesium atom is 3s2. That means we need to draw electron orbitals up to and including 3s. So we do 1s, 2s, 2p, 3s, 3p. Oh, we don't need 3p, sorry, went too far. We only go up to 3s. And remember, Aufbau's principle, which states we fill electrons by occupying each orbital before we go back to pair them. So it looks a bit more like this. Notice how I fill 2p, and then I go back, and 3s, we said there's 2. Using words, or sorry, not words, but just numbers and letters, we'd say 1s2, 2s2, 2p6, and 3s2. In core or shorthand notation, we'd locate the nearest noble gas, which in this case is neon. So up until 2p6, we call this neon in square brackets. And we could say 3s2. And these are the three different ways to give an electron configuration. Let's try one with a D block element. Say scandium. Scandium is a good one. So with scandium, we can see that it's found in the D block at n equals 4, except when we think D block, we always think n minus 1. So it's actually found in the third sublevel at D. So we could say 3D. And because it's in the first column of the D block, we say there's only 1 electron. So that would mean we'd fill orbitals up to and including 3D. So let's do that. So we have 1s, 2s, 2p, 3s, 3p, 4s, and then 3d. And then after that, oh, yo, sorry guys, I think I cut off there. Just let me continue off from here. So I think we were with scandium. Now with scandium, we were talking about drawing orbitals up till 3D. And we know that the outer orbital only has, or the 3D orbital only has 1 electron. So we do everything up till, I guess, 3D1. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. And that works out because scandium has 21 electrons. If I asked you, or let me just label these, if I asked you after I label these, this would be 4s. If I asked you this question, how many valence electrons does scandium have? What would you say? At first instinct, people might say, well, we'd look at the orbital or we'd look at the sublevel with the highest energy level. And in this case, it would be 3D. But we actually don't do that. We actually look at the orbital in the outermost n level, or the outermost shell. In this case, it's 4s. So there would be 2 electrons in our valence shell. So that's something you might want to keep in mind. When we're talking about valence electrons, we're talking about electrons found in the outermost shell. If I had 4s and 4p, say I had 4s and 4p, and if my 4p had 2 electrons, I'd say that my valency was equal to 4, because there's 2 here and there's 2 here. So if I wanted to write this in shorthand notation, I'd find the nearest noble gas. In this case, it's argon, where argon is found at 3p6. So everything up to 3p would be argon, then 4s2, 3d1. Shorthand notation is also called core notation, so those two terms are interchangeable. Another example that maybe would be useful to do is going a bit more into ions. Okay, going a bit more into ions. So how do we do ions? Ions, if we recall, are pretty much charged atoms which either have more electrons than they should have or less electrons than they should have. In other words, it's pretty much the same principle as determining the electron configuration of typical atoms, except we consider the addition or loss of electrons. Let's do an example. Say we had O2 minus. And just for the purposes of this demonstration, I think I will first give you the electron configuration of just regular oxygen. So for regular oxygen, if I wrote this in shorthand notation, we know that the nearest noble gas to oxygen is helium, so we can write helium. And then after helium, we have these two, which is 3s2, so 3s2. Then we have everything up till here, which is 3p3. Take a look, or before I do that, let me just draw 3s2, 3p6. I want you to take a look at the oxygen anion. You can see that there's a 2 minus charge. Well, what does that mean? It means there's an extra 2 electrons. Where would we put the electrons? We'd put it in our outermost orbital. So, we do this. That is essentially our electron configuration for our oxygen anion. So we'd write it like this. Helium, 3s2, 3p5. That's our new configuration. With aluminum, same idea. If it helps, you can always write the configuration of the neutral atom, the non-charged atom. If it helps, go for it. If you think you got used to it, you don't need to do it. But for visual purposes, if we look at aluminum, the nearest noble gas is neon, which is 3. Actually, no, it's 2p6. Okay? Because remember, n equals 2. So, from there, we can call 2p6. We can call 2p6. Everything up to 2p6 are neon, right? Our noble gas. And then from here to here, that's 3s2. And then up to aluminum, that's 3p1. So let's draw the box diagram. Box diagram looks a bit something like this. Notice the charge on aluminum is 3+, which means the aluminum cation loses 3 electrons. Therefore, these guys would go away, which means the electron configuration for aluminum 3+ is just neon. And that's a bit more about electron configurations of ions. So I hope that helped a bit. And if there's any other things you guys have concerns with, just feel free to hit me up. And yeah, hopefully that was helpful.